I'd like to talk to you today about my perspective as a neuroscientist about some of the topics raised by Oscar in the previous talk, and hopefully bridging the way to Danny's following talk. And we're all used to seeing these artificial limbs similar to what Oscar has just shown us, that frankly look as if a human and a robot has had a baby. And the question I want to explore, and I'm exploring with Danny Claude, is it really important for us when we are developing artificial body parts to stay very close to the biological body, or should we explore alternatives such as the vine arm that you see here that has been designed by Danny, and she'll talk about later in her talk, that doesn't look anything like the biological body but may afford interesting opportunities for functionality. And when you raise this question with clinicians and with engineers, the answer that usually pops up sooner or later is embodiment. The idea is that if we want to be good prosthesis users, it might be beneficial for us to relate to the prosthesis as if it was a part of our body, and for us to relate on an emotional and physical and cognitive level, we want to create something that looks very close to the biological body. So I'd like to explore with you this idea that to be a better prosthesis user, we want to see closer embodiment of the user to the artificial limb. But before I begin, I just want to throw a definition of embodiment. And here I'm using the definition of Frédéric de Villemont, who's a philosopher of the body. And she says embodiment is the ability to process information through external objects at any levels that you choose. So it could be sensory, motor, affective, etc., in the same way as the properties of one's own body part. And this is still a pretty broad definition, so we can unpack it to various facets of embodiment. We can talk about the experiential level. How does it feel like for me as a prosthesis user to relate to the prosthesis? Does it feel like a part of me? We can talk about the behavioral level. How do I act and react with my artificial limb? Would I do the same thing with my own body? And then we can talk about the neural level, which would ask, does my brain represent this artificial limb in the same way as it would a biological body part? So let's start with the experiential level, which is the easiest for us to measure. All we have to do is ask people how they relate to the artificial limb. And here we're using an adapted questionnaire, an adapted version of the rubber hand illusion that Oscar just presented. How do I use the laser? Okay. All right, great. So what you see here, oops, I don't know, it brings me back. Let's try here. So what we see here is people's responses from agree strongly to disagree to statements as something like, it seems like the prosthesis is a part of my body or a part of my hand. And each dot here is one participant responding to these questions. And as you can see, there's a huge variability across participants. Some people relate very strongly to these statements. Other people disagree with it strongly. But if we plot this against how much people use prosthesis in their daily life, we can see that there's a clear relationship. Those people who use the prosthesis more in daily life also tend to agree more strongly that they feel like the prosthesis is a part of them. So we have a relationship here between how people feel about their prosthesis and how functionally they use them in everyday life. But we have to be very careful when addressing these first-person accounts, which have been known to be very biased. So we were looking for another measure, more objective measure of embodiment, which led us to this really rich and interesting literature of gesture. So gestures are a way we use our hands to co-accompany speech and emphasize ideas. Politicians love to do it, but not just. Pretty much everyone does it. Blind people do it. You would do it while speaking on the phone, even though no one can see you. So it's a really ubiquitous form of using our hands, and we wanted to know whether amputees would use their prosthesis while speaking. So in this study, we invited participants to the lab, and we've asked them to watch a short cartoon video. And after they finished watching the cartoon, we've asked them to explain to us what happened in the video clip. And we have these measurements of acceleration in order to see how much they use. So the intact hand would be in red, and the prosthetic would be here in blue. And they don't know what the study is about. We're just asking them to express what they've just seen. And you're going to see up here the measurement of the accelerometers. And here, just for your benefit, I'm also going to show you what the participant has just seen and now recalling. Is the volume up for the video? Cool.
It was the cat off, I don't know what the cat's called, on Tweety Pie, and he was after Tweety Pie, he was at the top of the building. So he goes up the drain pipe. Tweety Pie sees him coming up the drain pipe. Someone goes and gets a bowling ball, puts the bowling ball into the drain pipe. Halfway up, the cat's halfway up. So he must swallow the bowling ball, and the bowling ball pushes him all the way down, out the end of the drain pipe, then down the street, and it rolls into the bowling alley.
All right, so as you've noticed, the participant was leading with his intact hand. But when the story was getting really good, like with up the drain pipe and down the drain pipe, it was also incorporating his artificial limb. And this is kind of what we see in the population. So here you see control participants moving their dominant versus non-dominant hand pretty equal. Here we have prosthesis users using their intact hand versus their prosthesis. So they use their intact hand more, but they also use their prosthesis quite a bit. Here's another measure. So this is a measure of how expansive the gesture is. And for control participants, here on the x-axis, we would see pretty much equal gesturing across the two hands. For amputees, we see an over-expression with the intact hand relative to the prosthesis. And here again, the results are plotted against how much people use their prosthesis in daily life. And again, we find that people that use their prosthesis more in daily life also tend to use both hands more equally. So here we have another measure, maybe an implicit measure of embodiment. People who use their prosthesis more would also feel more comfortable to express themselves with their prosthesis. But here again, correlation doesn't infer causation. We have to be careful with how we interpret these results. It's possible that people that use their prosthesis more in daily life take better care to fit the socket, for example, of the prosthesis to the residual arm, making it easier for them to make these big movements. So we were looking for another measurement of embodiment that doesn't directly depend on people's ability to physically use the prosthesis. Which led us to the visual cortex, where we and others have shown we have brain areas that respond more strongly when we show people images of upper limbs in comparison to other body part and object categories. So we can very easily pinpoint these areas in individual participants simply by contrasting images of hands to images of objects. And now we can ask within these hand-selective areas, what will be the responses when we're showing people images of artificial limbs? And here we have the cosmetic prosthetics that are aesthetically designed to mimic the appearance of a hand, and the functional prostheses that don't tend to look like hands. In our cohort, looked more like hooks, but still provide hand functionality. And if we just look at activity level within these visual hand-selective areas, when we're showing people pictures of other people's prosthetics, and these are the others' functional prosthetics, if we carefully select for prosthesis users, we clearly see more engagement in these traditional hand areas when people are processing information relating to artificial limbs. But does this mean that people embody artificial limbs as if they were biological body parts? To address this question, we used a brain decoding approach where we can compare the patterns associated with representing these different categories. And here I'm showing you the similarity in the representational patterns in control participants. And this is again in these body selective areas. So for control participants, a cosmetic prosthetics is represented very similarly to a hand, whereas the functional prosthesis that doesn't look like a hand is represented a lot more like a tool. In other words, the visual features of the prosthesis seems to determine how it is represented for control participants. Makes sense. What about prosthesis users? So here we have 32 prosthesis users. Half of them were born without a hand. The other half are acquired amputees. I'll show you the breakup in a minute. On average, we see that neither the cosmetic prosthesis nor the functional prosthesis is represented like a hand. It's not represented like a tool either. Instead, we see that the cosmetic and the functional prosthetics are represented more closely to each other. So it's almost like we have this breakage from the natural anchors, the tools and the hands, to create a new distinct category, which is artificial limbs. And here you see individual participants, the congenital and the acquired users. And what we show you here is how distinct the representation of the prosthetics is from both hands and tools, and how similar it is with each other. So how well we can articulate the representation of prosthetics in the brain. And this is plotted against prosthesis use as before. And what we find here is that people that use the prosthesis more in daily life, these are the people that tell us that they feel like the prosthesis is a part of their body, the people that gesture more with their prosthesis when they're speaking. These people actually show more distinct representation of the prosthetics away from hands and away from tools. So kind of the opposite of embodiment, more unique, distinct representation of a prosthesis as an artificial limb and not as a body part. And I think this is an important result because we are still looking at these brain areas that are body selective, meaning in order to take best advantage of these brain areas that were designed through evolution and our early life experience to represent the body, we don't necessarily need to treat the prosthesis as a biological body part. Brain plasticity would allow the brain other solutions. So this is all in visual cortex. What about actual control strategies? And when we think about controlling an artificial limb, we tend to try to be as biomimetic as we can. What does it mean? When Oscar is asking his participant to control his bionic limb, he would ask him to try and think about opening his biological hand in order to open the artificial limb, and close the biological hand in order to close the artificial limb, and so on. But we can also think in contrast as the completely arbitrary mapping, where in order to achieve a particular gesture with the artificial limb, the hand can perform a completely different non-related movement. For example, 1 in order to open the artificial limb, 2 in order to close the artificial limb. And we wanted to run a study to compare between as close as possible biomimetic approach to a completely arbitrary approach in order to determine what are the potential opportunities but also limitations of the biomimetic approach. So this is our technical setup. We ran it in able participant because we wanted to know exactly what the hand is doing. Here we're using an EMG readout, so similar to what Oscar have shown you, but from the muscles that normally control the hand. And this is in order to control an off-the-shelf artificial limb using the OeAW system. So this is just a video to show you what I've just described to you. Biomimetic, to close the hand, I'm closing a biological hand. With arbitrary, I perform a predetermined movement in order to achieve a particular gesture. So here you see participants training over 4 days in different groups. One group is trained with an arbitrary approach. The other group is trained with a biomimetic approach. And in the task that I'm showing you here, speed matters. So you need to pick up and transport as many objects as you can in a given time window. And here we see a clear achievement for the biomimetic group relative to the arbitrary group. They're starting much faster. Over time, the arbitrary group tends to catch up, but there's a clear advantage to using something that is familiar in order to operate the prosthesis. But this is a very crude, simple movement. What about more precise movement that needs to be controlled with greater finesse and dexterity? So this is our virtual egg task, where participants have to pick up and transport a fragile object. Press too hard, you smash it. Don't press hard enough, it will slip. So this is what we call a proportional control task. We have to really control the amount of pressure using our muscle signal. And in this task, there's no difference between the two groups. They tend to learn at the same pace. And this gives us an opportunity to ask, if you've learned for 4 days to control your artificial limb using one of the two strategies, how well will you be able to generalize from what you've learned so far to a slight change in the control strategy? So after the 4 days of training, we're introducing participants with a new strategy that is not entirely arbitrary, but it's also not strictly biomimetic. And what we find here is that for the arbitrary group, however much they've learned over the 4 days, they can fully transfer to the new gesture. So they know how to control something in an arbitrary strategy, and a small or different approach to arbitrary doesn't matter much. But if you look at the biomimetic group, if you give them something that is not fully biomimetic, they basically start to learn again from scratch. So 4 days of proportional control of this weird avatar arm has not prepared them at all to a small change in circumstances, meaning I believe that the biomimetic approach is not as versatile, it's more limited than the arbitrary learning. So to summarize, I think what I want to take from all of this is that biomimicry offers wonderful opportunities and wonderful inspiration, and something we should absolutely explore going forward with artificial limbs. But this shouldn't be our only approach. We can also try and understand what are the fundamental principles underlying successful motor control, and try to distill it and abstract it in order to potentially afford alternative approaches, alternative materials, and alternative designs, which could use us in order to achieve our everyday goals. And I hope this is a good bridge to Danny's talk. I just want to thank my wonderful lab in Cambridge. Thank you.